Now we're going to talk about forced vibrations. The easiest way to think about it is think about a child on a swing and someone is pushing them. Let's say the dad is pushing the child on the swing and they're pushing at some regular interval. Yeah? So that's a forced vibration that he is providing the swing and the child. Now, the swing and the child system will have a natural frequency. Okay? Everything has a natural frequency. This table, the chair, your bones, everything has a natural frequency. When there's an external frequency that matches your frequency, your natural frequency, we get a large uptake of energy, a large increase in amplitude of the vibration, and that phenomenon is called resonance. Okay, you might have sometimes heard this in your car when you're playing music and suddenly the sides of the car appear to boom. That's resonance that's going on. Okay. If we consider 3 simple pendulums which are connected, four, which are connected through a rod in a way that the vibrations can travel through the rod to each of them. And let's say I start oscillating this one at a certain frequency. Now we know for simple pendulum that the frequency depends on L, the length of the pendulum, and G. Yeah, so G is fixed. So it just depends on L, the length. So once this starts oscillating, the other ones will begin to oscillate, but the only one that will actually pick up the same large amount of energy is C, because it has exactly the same length. D and B do not have the same length. Therefore, those oscillations will get damped out in B and D, but not for C. Okay? This is a very famous showcase where a diva tries to sing to break the glass. So she's going to match her frequency to the natural frequency of the glass, where the glass begins to get oscillations in it. The particles in the glass start oscillating more and more as she comes close to resonance. And at resonance, they're oscillating so much that the glass actually cracks. This is a demonstration that a few divas like to do. Okay. Next, we come to standing waves in air columns. So just like we did standing waves in strings, you can actually get standing waves in an air column, and it could either be closed at both ends or closed at just one end and open at the other. So let's first take the case where it's open at one end. That means the particles are free to move. So we are always going to get an antinode where the particles are very free to move. So we're going to have an antinode here, the widest part of our segment. And we're going to have a node where the particles are touching the closed end. So this end is closed, this end is open, yeah? This would be the longest wavelength that we can have in this column, air column, or the lowest frequency, yeah? So that's going to be the fundamental frequency. You will then get other harmonics. This is my first harmonic. This is 1/4 of the wavelength, right? Do you see that? This is 1/4 of a wave. So lambda equals 4 times L, where L is the length of the tube, or the frequency, which is wave velocity divided by lambda, V divided by 4L. Yeah? Then the next one that you can get if you change your frequency is you can get 1.5, right? So that's 3/4 of the wave has fitted in here. Yeah? Only 1/4 is outside. Why does that happen? We're not able to get n equals 2 because we can't get nodes on both sides. This side has to be an antinode. So if we just fitted one node, this is where we'd have to cut off, yeah? But that won't work. So we have to get an antinode at the open end. So we can't get n equals 2, 4, and so on. You can only get odd multiples of n. This is very important to note, this difference that will arise between one end open, and we'll see what happens when both ends are closed. Then obviously you can get a second node here. And so every harmonic should be possible. But now you get first harmonic, third harmonic, fifth harmonic, yeah? And you don't get the second and fourth. So lambda equals 4L over 3 here, and you can convert to find what the frequency is. The frequency will be 3 times the fundamental frequency. Yeah? And here it will be 5 times the fundamental frequency. So you need to be able to do these. You need to be able to draw the diagrams. You need to know that in this case of one end open, we get only odd harmonics, okay? So the general formula, Fn, n equals n times F1, where n is 1, 3, 5, etc., only odd numbers, no even multiples. And this is the same thing shown, sorry, both. Okay, sorry. This is the case where both ends are open, okay? So in this case, we can get antinode here and antinode here. We are seeing half the wavelength here, yeah? The other half is missing on both sides. So we have lambda equals 2L, yeah? And you can find F1 from there correspondingly, yeah, as V over 2L. How much of the wave is fitted here? We have one entire wavelength, yeah? I hope you're able to see this. And then we have fitted one entire wavelength and then a half. So we have 1.5, we have 2 over 3. 3 over 2 wavelengths, or lambda equals 2 over 3L, yeah? Okay, so now we see that we're able to get every harmonic, yeah, when both sides are open. So Fn is now n times F1, n equals 1, 2, 3, and so on, yeah? Let's do a simple problem on this. What length should a tube closed at one end have on a day when the temperature is 22 degrees Celsius if its fundamental frequency is to be 128 Hertz? That's the C below middle C. Take the speed of sound in air at 0 degrees Celsius to be 331. So the first thing you want to do is to find the velocity of sound, okay, because you're going to need it in your formula, at that given temperature of 22. So you're going to use this formula to find the velocity. It's going to be greater than 331, right? We did this before, so I'm not going to repeat this. You're going to find that velocity, and then you're going to plug it into this formula. You need to find L for Fn, the fundamental frequency, which is n equals 1, as 128. And then you can solve for L. And if you do that, you should get L equals 0.67 meters.